real, it's the next episode.
Well, welcome back. In this episode, we're going to install this copper sheet that we made in the last episode. So if you haven't seen it, feel free to check that out. The intention is to try to improve ABS print on this cheap 3D printer. And I think that using copper is going to give us faster heat up, a more uniform heat displacement around the actual bed from corner to corner. So why don't we just begin with assembling this, heat it up. Let's check the temperature from corner to corner, and then we'll do a test 3D print to see how that fares. So the assembly is rather straightforward. The whole bed sits on these springs. You install the heating element, so I need to plug that in first of all. Like so. You then install your copper sheet on top of that as well. Okay. You begin to insert your countersunk screws through the spring and at the other end of the bed holder. There we go. Let's raise the whole lot up as high as we can. And then next step is to install the thumb screws at the bottom to keep everything in place. This is also extremely fiddly because you can't see the damn thing. There's one. Two. 3. There we go. Now just tighten them all up. I'm going to use a screwdriver. I've got a tool that I've made, and I'll show you how I adjust the beds and how I level the beds. Obviously there's no auto leveling on here. I don't think it needs all the time. There we go, let's just switch that on. I must try to sort that fan out at some point, it's just bloody annoying. Okay, the last thing is the actual glass itself. Let's put that on the actual copper plate. And we use these kind of bulldog clips to clip it in place. So that's easier to remove when I need to remove the actual model from the glass once it's printed. And obviously clean this glass up as well. I use isopropanol, make sure it's grease free. And what we'll do is we'll do a test print on the actual bare glass and see if that bonds to the glass in any way. So to adjust the bed and level the bed, typically people use a piece of paper, for example like this post-it note, and they guess that it's going to be about 20 microns. No, well that's just stupid. Let's get rid of that. The best way to do it, in my opinion, is use something a bit more professional, a feeler gauge. Just a couple of quid from your local hardware store, and each of these have a varying thickness, and it's called a feeler gauge for that one reason, because you do exactly what you do with the piece of paper. You put that under the nozzle. This is calibrated, if you can see it, to 20 microns, and then you can put that underneath there, feel it until it touches it. It has some resistance. Job done. And I also use this item here as well, which is a digital micrometer. What I've done is I bought this. This is typically what they use on a milling machine or a grinding machine, and I created this stand for it. So they sit on the actual rails. They've got these magnets on it. This channel here is to miss the belt, the GT2 belt, and this is for the linear sliders. So the next step is to level the bed to the nozzle. So let's home the axes first, bring that bed up. And I always like to heat the bed up as well, because at the end of the day, we're talking microns here, and through thermal expansion, that's exactly what could happen. We could adjust things by microns, which throws everything off. So I'm going to heat up the nozzle and the bed, and we'll just wait for that to heat up. Right, that's heated up sufficiently. All we do is stick this menu onto level the bed. There we go. So what that will do is it's where it thinks it should be level. We move the nozzle onto the bed, up to the edge. Oh, that's not too bad, you could guess. Get some of this crud. Right, you get your feeler gauge. I tend to put the nozzle right above the adjustment screw. I've got my feeler gauge here, and I can tell, oh, that's very good actually, and that needs to be loosened a bit. There we go, I can feel it now. There we go. So that's 20 microns. Okay. Now, if I move this totally out of the way, like so. So from that point of reference, now we know it's level, I can introduce my micrometer. I'll put that on the rail and put it above that reference point, which is the screw in this case. Switch it on. I can zero it at that point there, which is above the screw. Even me touching it can distort the actual readings. So I can move that across to the other screw, which is the other adjustment point, and it's telling me it is 16 microns off. So this is a case of loosening it because it's too far low, which will raise the bed, and making it zero there. Right, so we've done that one. I can now move that forward. And this is telling me it's now 33 microns too low. So again, I'll loosen that off till we get to 0 again, which is very fiddly. 7 microns, 6, 4, there we go, that's 0. And I'll move that across the other point, the last fourth point, and that's showing 9 microns. We need to loosen that. Six, 3, 0. Okay, so we check it again one more time, and we need to try to get it back to 0. So this is now showing too high. So what's happened is that when we adjust the other points, it acts like a seesaw. So one end will actually pick up and the other one will drop down again. So what we do is we go around again, adjust it one more time, get it to 0. That's 0, which is fairly good. You can't see that, but it's telling me it's 13. Well, you basically go around like that and you adjust it. Well, let's do a test print. The menu. Let's find a flat model. That'll do. Print. Here we go. We'll just clean the nozzle by drawing a line. And it's looking like it's level. Well, clearly that is not sticking in the slightest. There you go. Zero sticking. Let's cancel that. Go to plan B. Plan B is use Acetone tape. So I've just installed the glass sheet now with the Acetone tape, and we'll do another test print. It's looking good so far. It's just started the second layer and it seems to be sticking down quite well. And it seems to be laying it down quite smoothly, fairly flat. There's no bubbles, no distortions of any kind. So let's see if the third layer is going to have an effect on it. Just doing the supports there. Yeah, still flat. Very good. Well, there you go. It seems to have worked. Plan C is, if it didn't work, I would have used kind of a acetone slurry mix. You can't see it here, but it would have been. I think that would have worked with the Acetone tape. It probably would have worked with the glass on its own. Let this print, see what happens. I think the next thing to see is how easy is it to remove. Is it going to be difficult or is it going to be easy? So it's finished printing, and I've allowed the glass to cool down. So in theory, it should be quite easy to take off. It should just peel away. So if I'll pinch one side, pinch the other side. Hope it doesn't break. There we go. Look at that. It's so smooth on that back. It's kind of almost brought the tape back up, but you want it to stick at the end of the day. That's the important thing, and it is a large flat surface that was stuck down. But looking at the quality of the print, it's looking very good, very flat. There's no pockets of air whatsoever. Yeah, quite happy with that actually. There you go. I think we got relatively good success out of that, and I've got two pieces of glass and they've both got Acetone tape on it, so while one is cooling down, another one can be printing, and so on. So now that we got the printer finally printing ABS, I wanted to use it for a real life application. This is a part for a light hood Having dug out the loft and brought it down, the reason it was in the loft is because it was broken. So this part would actually engage onto the actual light hood here, and then this part here, this part here would then go onto the actual stand that would hold the light hood up. Without this part, the light hood is basically ruined. It won't be able to work. So I'm going to CAD this up very quickly, and then we'll print it out and see how we can get this thing to work. Let's do it. So with any of this, the first thing to do is obviously model it up in any CAD package. I've used a software called Inventor by Autodesk. It's something I'm very familiar with, and I find it very comfortable to work with. So taking measurements from the part that's broken, and more or less taking measurements from the stand, and understanding how that mechanism is put together, I kind of designed half my own and half what was broken. With the design, you have to think about how it's going to print it as well. So no major overhangs, and there's got obviously these ribs on the side to hopefully further strengthen this design up. So here's the replacement part for my broken brackets for my light hood, and it's printed it very successfully. Now the issue we have is that this will be a mechanical part. What that means that they'll be fixed using screws, and they'll be under compressive and tensile loads, so there'll be a mechanical load all over this, which is not the best situation for 3D printed parts. You can see there's a nut that will go in there. That will be screwed through, the pole will go through here, you tighten it up, and that will fix itself to the pole. On this side you'll have a nut and another screw that will then clamp around the bracket for the light hood. Now this way, because it's printed in a ring fashion like so, when it's under compressive load, it's actually not too bad because it's got no weak points. The actual material strength of the ABS is what you're going to be fighting against. But when you're going up against the actual layer, then what you're depending on is the fused material with the next layer. So I think the best analogy you can give this is if you take timber, a plank of wood, and you try to break it across the grain, it's very difficult. But if you try to split it through the grain, it's quite easy to actually split that. And this is no different. This is the same thing. So here you can see that this is the weakest point here. There doesn't take much to actually snap that. I can snap that end off as well. There we go. Crap. There we go, the inside bit. So yeah, pretty crap when it comes to doing mechanical fixes. So the best way I feel that the way to tackle this issue is to deal with the actual layers and try to get the layers to further fuse together, so that it's mechanically more stronger and you're not depending on the actual weakness between the layers, the bond between the layers. So the best way to do this is use some acetone, put it in the dish. I use a Pyrex dish with a lid, and I actually stick this through my heated bed. I heat the bed up to 110 degrees. I leave it in there, not for that long, probably 30 seconds, 20 seconds. It's up to you how you judge this. And I do rotate it so that it does, the acetone vapor cloud does surround the whole of the component. This component is would be even more stronger. It should be mechanically stronger. It should be mechanically more robust and do the trick. And also it creates a neat little shiny surface, although not to manufacturing standard, but it's fairly good. So there you go. Those people who don't believe in 3D printers and thinks it's just a fad, it's a waste of time, waste of money. It allows you to actually create a parts bin for any component, any product that you have that has failed. So in this case, these light hoods I use, they would have gone in the bin. The manufacturer's probably gone out of business. There's no way I could have made this out of wood, and it probably would have looked unsightly. So this now gives me the ability to 3D print as many spare parts as I want, and this file is now stored on the SD card. Should it go again, just press print and job done.